If you've ever heard a DJ drop an a cappella track over a totally new beat, or maybe watched a video editor pull music away from dialogue in a trailer, you've seen music source separation in action.
You have, yeah.
And today we are doing a deep dive into stem splitting. That's the tech that can basically reverse engineer a finished song and just explode it back out into its core tracks, vocals, drums, bass, all of it.
And our mission here is to really guide you through the latest stuff, the AI-driven vocal isolation breakthroughs. We're going to move past the simple separation, get right into the technical, the practical, and even the legal challenges.
Okay.
We really want to show you how researchers are finally starting to solve that one persistent quality-killing problem: audio artifacts.
Right, the artifacts. We've got a whole stack of sources here that they perfectly capture this tension.
Yeah.
So imagine you're a creator, you're using a new AI platform, something like Udio. You generate this amazing instrumental, you layer on some new AI lyrics, and you're blown away by how good it sounds. But then you take that mixed track and try to isolate just the vocals.
And that's where it all falls apart.
That's where the trouble starts, exactly.
Exactly. The sources are really clear on this. The instrumental might be perfect, but that vocal stem you pull out is often, and this is a quote, saturated with artifacts.
Saturated.
It sounds crackly, or there's this weird bitrate mismatch. It just makes the AI source painfully obvious when you put it against a clean background. It's the ultimate paradox. AI can create something amazing, but it can fail when you ask it to perfectly uncreate it.
That paradox is exactly why this whole field, music source separation, or MSS, had to evolve so fast. You said it's been around for decades, though, so how did we even do this back in the day, before neural networks?
Well, MSS is actually a specialized branch of signal separation. It got its start back in the mid-1990s.
Oh, that early.
Yeah. And at first, the uses were very professional. We're talking remixing, remastering, audio restoration. Now it's also huge for licensing. Think of a TV editor who needs to pull a vocal out of a song so it doesn't clash with the show's dialogue.
So if the goal was separation and there was no AI, what was the first big trick that engineers used?
The foundational method, the traditional one, was phase cancellation.
Phase cancellation. Okay, that's the physics concept, right? Where sound waves can literally destroy each other.
Precisely. Phase cancellation happens when you combine two sound signals that have the exact same waveform, but one is flipped 180 degrees out of phase.
So the peaks of one signal line up with the troughs of the other.
Exactly. And when they combine, they cancel out. You get silence.
And the practical application for vocals was, it was brilliant. If you had the original mix song and you also had an identical instrumental version,
which labels often released. Yeah.
Right, on a CD or vinyl single, you could just flip the phase of that instrumental track.
And all the instrumentation in both files would just cancel itself out, leaving only the sound that was unique to the mixed song.
The vocals.
The vocals. It was smart, but it was so conditional. It only really worked well if the vocal was perfectly dry and recorded in mono.
Oh, okay.
If the singer's voice had a ton of reverb, or if the vocals were panned around, which is common, the cancellation would just fail completely. You'd be left with this messy, ghostly sound.
Which means for any complex track, you were basically relying on the second method. Good old-fashioned studio access.
Pretty much. You either used the official acapellas or you had to be a producer with connections. Someone who could call the label and get the actual multi-track tapes or the session files.
And that's when the AI revolution really kicked off.
That's when everything changed. Deep learning models, you hear names like WaveUNet, Spleeter, Dimix. They're trained on these huge data sets with millions of pre-isolated stems from real projects.
So instead of physics tricks, the models just learn to guess what the vocal sounds like.
They learn to estimate the source components directly from the final mix. And what was once a studio secret is now just available to anyone.
Yeah, these tools are everywhere. Standalone programs like UVR5, built-in features in Logic Pro. You can even do it right in your browser now with tools like lal.ai.
It's completely democratized.
Okay, so let's get back to that core user problem, the artifacts. Why does the AI, after all this incredible training, still struggle to give us a clean vocal?
It really comes down to frequency overlap.
Yeah.
And the compromises the AI has to make when it first creates the mix.
Okay.
Our sources pointed out that when a platform like Udio makes a mix, it often blends vocal frequencies with other instruments. And this creates something engineers call spectral bleed.
Spectrally, that sounds like a ghost image on an old TV.
That's a great analogy.
Yeah.
Imagine the sound spectrum as a canvas. The AI tries to paint the vocal in one area, the guitar in another, but their colors, their frequencies, they get mixed together at the edges. So when you tell the separation model, hey, just give me the vocal, it has to try and pull that blended paint out. If it pulls too little, the vocal sounds thin and hollow.
And if it pulls too much?
It drags fragments of the guitar or the cymbals with it. And that's what we hear as crackles or noise.
So the model is making this educated guess, right? It's saying, I think this little bit of sound is, say, 85% vocal.
So I'll put it in the vocal stem, but that other 15% is the artifact we hear.
Exactly. And the sources say when users then try to manually clean that up, with EQ or noise reduction, they just create gaps in the song. They end up cutting out parts of the actual vocal by accident.
It's a really difficult balancing act.
So faced with this, users have come up with some pretty creative ways to just hide the artifacts in the mix. It's almost like putting an Instagram filter on a photo to hide the flaws.
That's a perfect way to put it, yeah. One of the most common sort of low-tech fixes producers mention is just bathing the vocals in lots of reverb.
Reverb. Why does reverb work so well for hiding these specific flaws?
Because the artifacts are basically high-frequency digital noise. Little clicks and weird phase issues. Reverb, which is just the decay of sound in a space, it intentionally smears and blurs the lines between sounds.
So it just washes everything out.
It washes out that sharp digital crackle and replaces it with this smooth, decaying noise that our ears just accept as natural. It's sonic camouflage.
And some of the other solutions are more genre-specific, right? Like using stutter or glitch effects.
Oh, absolutely. Glitch effects are huge in genres like trance or experimental electronic music because the music itself already embraces that kind of controlled distortion and noise.
So you just lean into it.
You just lean into it. If your vocal stem has a little digital roughness, you just frame it as an artistic choice.
Yeah.
You're turning a bug into a feature.
But okay, if you want professional quality, you don't want to just mask the problem. You need to look at post-processing solutions inside the tools themselves.
And this is where the really advanced options come in. The most powerful tools, something like UVR5, have what's called an ensemble mode.
Ensemble mode.
So instead of running just one AI model, ensemble mode runs several different models at the same time. Maybe one is great with bass, another is trained specifically on high-frequency vocals. It then averages their results together.
That makes a ton of sense. You're basically letting multiple AIs vote on where each little piece of sound belongs.
Exactly. You're taking the consensus to smooth out the errors that any one single model would make.
And for the absolute most control.
Then you move into what are called spectral editing doggies, things like RipX or spectral layers. These don't show you a normal audio waveform. They show you a note-based harmonic structure, kind of like a piano roll.
So instead of that big blue blob of sound, I'm seeing like individual colored blocks for each note and its overtones.
Yes, you can literally zoom in and see that tiny bit of guitar bleed at 4 kilohertz as its own little colored shape. And then you can use the tool to manually erase it or turn it down or even move it somewhere else.
Wow.
It allows for surgical cleanup that no automated process can match. But, I mean, it is incredibly time intensive.
Okay, let's unpack this and get into the real technical weeds here. Because to really appreciate the solutions, we have to understand the science of why the artifacts happen and how we even measure quality. We need to look at the theoretical limit of separation.
So we start with the benchmark. It's called the ideal binary mask, or IBM. The IBM represents the theoretical perfect performance for any separation system. Think of it as the perfect answer key.
The answer key. How does that work in practice?
Well, it functions as a perfect classifier. It would theoretically assign every single tiny time frequency element in a mix to its correct source vocal or not vocal with 100% accuracy.
Nobody can actually achieve it, but it's the goal.
It's the goal the models are trained to estimate. And early deep neural networks, the DNNs, they started getting closer to estimating this IBM, and they just blew past the traditional methods. Researchers trained these convolutional DNNs and compared them to older methods like non-negative matrix factorization, or NMF. NMF is very rigid. It's like solving an algebra equation. The DNN, on the other hand, uses complex, nonlinear learning.
And what was the measurable difference? I mean, how much better was it?
It was substantial. The DNN approach gave them about 3 dB better signal-to-artifact ratio, or SAR, for a given signal-to-interference ratio, or SAR.
Okay, let's quickly define this. SIR is how well the vocal is separated from the other instruments, the interference. So what's SAR?
SAR measures the purity of the thing you isolated.
Well,
It's the ratio of the signal the unwanted artifacts created by the separation process itself, and a 3 dB gain in SAR. I mean, that's a really noticeable difference in noise.
so the DNNs just delivered a much cleaner stem, less hiss, less distortion.
Significantly less. And the gain was even bigger for the human voice. The DNNs showed a 5 dB advantage specifically for vocals. It proved they were way better at spotting the abstract patterns of a voice in a dense mix.
Okay, but this is where it gets really interesting for me. Because even with the power of DNNs and transformers, this new challenge popped up that hit the AI's core weakness: intermittent vocals.
Yes.
We're talking about really sparse vocals, a single word, a quick sample, something that just shows up irregularly.
This is a huge, huge problem for transformer models. Their core mechanism is global attention. A transformer is designed to spread its focus uniformly across the entire piece of audio you give it.
So if you give it an 8-second clip where a vocal only appears for 1 second,
It wastes a ton of processing power paying attention to the 7 seconds of silence or drums.
it's like using a giant floodlight to find a tiny key on a football field.
That's a perfect analogy. The important vocal information, the tokens, they just get diluted by all the attention being paid to the irrelevant noise around them, and the separation quality plummets in those sparse moments.
So the solution to this uniform attention problem had to be something completely different.
It is. The new frontier is a model called BS Mamba 2. And what it does is it radically replaces the standard transformer parts with something called Mamba 2, which is a specialized state space model, or SSM.
Okay.
The game changer is its system of selective state updates.
Selective state update, so it learns to ignore what it doesn't need.
Precisely. Unlike a transformer, Mamba 2's parameters are input dependent, so the model can dynamically decide where to focus its attention. When a vocal token appears, it ramps up its focus, information flows strongly. When the vocal is gone, Mamba 2 just suppresses or ignores that irrelevant information.
It's like adaptive filtering in real time. And what did that actually achieve? What were the results?
The results were pretty definitive. BS Mamba 2 got the best reported chunk-level signal-to-distortion ratio, or CSDR, to date, 11.03 dB.
Wow.
And that CSDR is a really high-fidelity measure of cleanliness. But more importantly, it almost completely got rid of the performance drop that older models had with those short, sparse vocal bits. It proved that selective attention is the future.
And to put that 11.03 dB into perspective for you listening, that level of performance means the separation is so clean that in many cases the human ear would struggle to tell the difference between the AI stem and a real studio a cappella.
It's an enormous leap.
It really is.
Yep.
So, what does this all mean for you, the learner? We have these incredibly powerful tools now thanks to models like Mamba 2. But we have to talk about the legal side. You've got your perfect vocal stem. What can you actually do with it?
And this is the copyright trap. Just because the tech lets you pull a pristine vocal from a copyrighted song, that doesn't give you the legal right to use it.
Right.
If you take those vocals and use them for commercial gain, a monetized YouTube video, a remix you sell on Bandcamp, you are breaking copyright law unless you get permission.
You can't just put a cappella by artist X in the description and call it a day?
Not at all. Attribution is not permission. For commercial use, you need a sync license from the publisher and a master use license from the record label. If you upload a remix without those, the Content ID systems will flag you instantly.
But there are some legal safe harbors, right? Things like fair use.
Correct. The law is generally on your side if you're using stems for purely educational purposes.
Yeah.
Breaking down a song to analyze music theory in a classroom. It's also often covered for things like commentary, criticism, or highly transformative works like parody, which don't really compete with the original song.
So for you, the learner, looking to experiment with this tech responsibly right now, what are the top tools you should be looking at?
Well, based on our sources, they fall into 3 main buckets. For pure standalone power and the most control, Ultimate Vocal Remover 5U VR5 is the top choice. That ensemble mode and its open source nature give you so much to work with.
And if you just want something quick, in a browser.
For browser-based quality, Audio Studio is highly recommended. I'd also say check out a site called MVSEP. It's fantastic because it has tons of documentation and lets you directly compare how different algorithms work on different songs.
Okay, good tip. And finally, for people who want to stay inside their DAW, their digital audio workstation.
For DAW integration, the best options are probably Landar stems. which is a plugin that works with most systems. Or if you're on a newer Apple Silicon Mac, Logic Pro's built-in stem splitter is really, really good. It's highly optimized.
It's incredible. We started this deep dive with simple phase cancellation, a clever audio trick, and we've ended up with selective state space models like Mamba 2 using adaptive attention to solve this huge challenge of intermittent sound.
I mean, the biggest takeaway here is that while quality still depends on the model, the genre, and the source file, the real gains now are coming from intelligence, not just brute force. The models have learned to focus, to only pay attention when the sound is actually there.
Maximizing purity and minimizing artifacts. So, if AI can learn the difference between a 1-second vocal clip and the noise around it with this level of adaptive precision, what other complex signal separation problems are going to become instant and error-free in the near future? Just think about what this could mean for forensics pulling a crucial piece of dialogue out of a chaotic recording, or for achieving perfect audio restoration of old, damaged historical recordings. That shift to selective processing, that power of adaptive focus, that's the real game changer here.